Most of us picture generating electrical power as a highly dynamic process. We expect a shifting, pulsing magnetic field, like an electromagnet turning on and off, to push current through a wire. The American physicist Joseph Henry, working independently around the same time as Michael Faraday, helped prove that changing magnetic fields induce electric currents. This diagram shows a classic thought experiment. We have a constant, uniform magnetic field. Inside it, we drag a metal rod across a U-shaped conducting rail. The magnetic field here is completely static. It isn't pulsing or fluctuating. Yet, the physical movement of the rod across the rails pushes charges through the metal, generating a measurable voltage. You don't always need a changing field to create electricity. Physically pushing a conductor through a static space works too. Physicists call this motional EMF. This animation shows a top-down view of our circuit. The sliding rod and the U-shaped rails form a single closed boundary, and we can measure the specific area enclosed inside it. That area has a fixed width, which is the length of our sliding rod. We'll call it L. The other dimension is the distance to the closed end of the rails, X. As the rod slides left, X shrinks. Because the physical boundary gets smaller, fewer magnetic field lines pass through it. The total magnetic flux, which is the measure of the total magnetic field passing through a given area, goes down. Faraday's law of induction states that an electromotive force, or EMF, is induced in any circuit whenever the magnetic flux through it changes with time. The total flux is simply the magnetic field strength, B, multiplied by the length, L, and that shrinking distance, X. Since X changes at the exact velocity of our sliding rod, V, the rate of change resolves into a neat formula. The induced voltage is exactly B times L times V. Looking at it macroscopically, the induced voltage is a direct geometric consequence. The circuit's area collapses through the magnetic field lines, and that shrinking space drives the current. Curious tone. Let's leave the circuit geometry behind and look strictly